Hi everybody, welcome to another section in Calculus 3. Section 14.5, curvature and normal vectors. This is not going to be a very long section. Right, before we start that section, I just want to back and modify one thing. This is section 14.3, page 35. So what I wrote is that circular motion in 2D and a line like this. And let's just graph and see what happened. Of course, that's still a circle, but parametric form. In radian. Right, I say A is 2. Yeah. Wait. Yeah, we have to go from 0 to 2 pi. So that's still a circle. The difference of this circle, okay, let's graph as traditional if we have cosine and sine. Let's put 3 cosine of t instead. So the bigger circle and 3 sine of t. Right. So first we have that circle and the circle on the outside. It's like that. Let's go back and change 1, 2. When we have that symbol, a dash and a circle. A dash and a circle. Right, let's see. So the first circle starting from 12 o'clock and go clockwise. So if we have this one, it is a circle start 12 o'clock and go clockwise. And this one start at 3 o'clock and go counterclockwise. But still a circle, right? But of course, standard usually we refer to cosine and sine. Yeah. More standard that way. All right. I will go to 14.5, curvatures and normal vector. So what is curvature? Yes, like I said, it is not a very long section, so we can go back and study a few things. So let R describe a smooth parameterized curve. If S denotes the arc length, of course we did that on the previous section, and then we write T as the velocity vector over the magnitude, that is the unit tangent vector. Because that's how we define it. In that case, the curvature is given by this formula, and that Greek letter kappa. That Greek letter kappa. Right, and that is the magnitude of the curvature is the magnitude of the rate at which the direction of t changes with respect to the arc length. So if we have the straight line, the curvature would be 0. If we have like an arc of a circle, if we have an arc, the curvature will be something, but a straight line curvature will be 0. Right. So loosely speaking, it is whatever the unit tangent vector, the direction where the unit tangent vector changes. The straight line, the unit tangent vector does not change. So that's why it is 0. Right. So that this is the Greek letter. Once again, is kappa. Right. Now, if you go to compute science, do anything with graphics and have to deal with curvature, then you have probably the whole page of formula how to calculate curvature. When I studied that in graduate school, I see the whole page like 10 or 15 of them. Just calculate the curvature. And so this is only one of the way we do it. So let R of t describe a smooth parameterized curve where t is any parameter. Then because that is the velocity vector or the tangent vector, and t is the unit tangent vector, then we have that. This is determined by the curvature. And this is another way to do that. Let R be the position vector or a parameterized curve. The curvature at the point on the curve is given by that. And we have, of course, velocity and acceleration. So probably we will use this one because we just need to find acceleration and velocity, do a cross product, and then we'll go from there, right? Right. Now we have a first example. Find the curvature and find the curvature of the parabola given like this. So first thing we do is find the acceleration vector, velocity vector, and then acceleration vector. So velocity, and this is just also a reminder that the vector I highly recommend that you follow this notation. When we go to the later chapters, it's very important. We look at the problem, we need to determine which one is that a vector or is that a scalar. So that is very important. The notation is very important. So we check derivative to find the velocity vector. Derivative of t is 1. Derivative of this is 2 at. Right, just derivative with respect to t. And then acceleration is the second derivative, will be 0 and 2a. Of course, we can write that as I plus 2at j, and then there's no I, just 2a j, right? Yep. And then we'll find the cross product. Usually when we find the cross product, we put in the determinant 3×3 determinant with ijk on the top and all that. But since this is simple enough, we just say this is a cross v. By the way, it doesn't matter because we have the magnitudes. It could be a cross v or v cross a. The magnitude would be the same. But we do the cross product first. Now I just do a cross v. A is 2aj, and then cross v I plus 2at j, and then we multiply like we normally do distributive. So 2a j cross I, 2a j cross I, and then plus 2a times 2at is 4 a square t, and then j cross j. So pretty much whatever the scalar function, we move to the front, like 2at and 2a, move everything in the front and multiply them, and then we have j cross j. Notice it's very important that we do not switch the order when we do the cross product. So exactly what we have. And then remember the cyclic relation I, j, k. This notation, I cross j is equal to k, k cross I is equal to j, j cross k is equal to I. So just go in that circle. And j cross j, anything cross itself is 0. Vector. Because vector, the cross product the magnitude is determined by the product of the magnitude times sine of the angle in between. If the angle of two identical vectors, the angle is 0, sine of 0 is 0. So that's why the magnitude is 0 and the vector is a 0 vector. J cross I, we go reverse. J cross I is go to negative k. So we just have 2a negative k or negative 2ak. Nice enough, right? Like I said, if it is only a few terms, just multiply it out. If it is the full 3 components, just put in the determinant. But this is simple enough, right? So we do that, and then we find the magnitudes of A cross V. So just negative 2A. It just have one component, right? So we just do that. Then 0 square doesn't do anything, right? And it would say, okay, A is positive. So in that case, this goes for A square, and since A is positive, square root should be positive, so we just have 2A. Now, did I mention that the notation is extremely important? This is the acceleration vector. This A is just A, right? So when we look at the problem, if we just write A all the way, difficult to see which one which, but make sure the notation is correct, then we don't have to worry about it. Right, so we have the top. Now try to find the magnitudes of V, the bottom. V is this vector, so we have the square root of 1 square plus 2at square. So it's 1 and then 4a square t square, right? And then the curvature kappa equal to the magnitude of the cross product of A cross V over V magnitude cube. So we just have 2A over, let's just say we're going to cube that. So simple enough. Find velocity vector, find acceleration vector, cross product, and then go from there. When I write the note, I didn't realize that we need more than one example, especially this example is too simple. So you don't need to write this down. Just go through this real quick. So find the curvature. So this is the problem. I just thought that we need an extra problem. That's all. I probably will not do this again. I try to have all the example in the note before I post online. Anyway, I'll find the curvature of this. So first, if you want to, we can write this as a component form: 10 plus 9 cosine 5t negative 1 negative 9 sine 5t and then 4. Usually I prefer to write this notation. It certainly will be easier to type in the note. All right. Velocity is the derivative of that. Cosine 5t, derivative is negative 5 sine 5t. Derivative of this is negative 9 5 cosine 5t. Derivative of 4 constant 0. So we have negative 45 sine of 5t, negative 45 cosine of 5t. And then let's find the acceleration vector. Derivative of sine 5t is 5 cosine 5t. By the way, I just got a bug on my fingers, so that's why it reacts like that. Cosine 5t, negative 5 sine of 5t, and derivative 0 is still 0. So we have negative 225 cosine 5t, 225 sine of 5t, and 0. Right. And then the cross product of A cross V, right? A cross V. It doesn't matter which one cross which one, but like I said, because we're going to take the magnitude later. So I component negative 45 sine of 5t, J negative 45 cosine of 5t, and K 0, and then A negative 225 cosine 5t, 225 sine of 5t, and then 0. This one, of course, we can also multiply like we did before, just don't have to use the determinant. Anyway, so now if we use the determinant, first cover the I component. Yeah, even though we have the 0, I still do that. Of course, always for the cross product, expand using the first row. So we will have negative 45 cosine 5t, 0, 225 sine of 5t, 0, I. For the J, it is minus, over that, negative 45 sine of 5t, 0, negative 225 cosine 5t, 0 in the J component, then plus that, try to put that here, negative 45 sine of 5t, negative 45 cosine 5t, negative 225 cosine 5t, 225 sine 5t, and then we multiply in the K component. Sorry, that K. Right. Next, cross multiply and subtract, multiply that to that, 0, subtract that, still 0. So I have nothing in the I component. J, once again we have 0, and K, 45 times 225. So it's going to be negative. Okay, let's just say plus negative 10,125, and then subtract also sine square 5t plus not plus, sorry, subtract negative and then subtract. So subtract negative times negative. So 3 negative sign still remain negative. 10,125 cosine square 5t k. So with 0, 0, we don't even need to write this. Factor out the negative 10,125 sine square plus cosine square times k, and because that's 1, so we just have negative 10,125 k. Right, magnitudes easy, only one component. The magnitude is just like the absolute values, pretty much. So A cross V magnitudes is just like that, or we just have the absolute values. Right, so that. So the first thing we do is find the cross product of A cross V, the magnitudes of the cross product of A cross V, and next we find V, and then magnitudes of V, and then cube, and then we just divide them. Magnitude of V, this is V, so we have square root of square of the component. So this is the V, and then 0 square. Right, 45 square, 2025. Oh, I don't even need to do that. 2025 sine square 5t, 2025 cosine square 5t, and then 0. And factor out 2025 cosine square plus sine square is 1. So we just have square root of 2025. Except we don't even need that. I just 45 square. So square root is 45. And finally, the curvature kappa equal to the cross product of A cross V over the magnitudes of V cubed. So we have 10, 125 over 45 cubed. And 125 45 cubed. We have 1 over 9. So the curvature is equal to 1 over 9. So it's not that bad. Yeah, but I thought I just need to do one extra example on that. So it's pretty straightforward to calculate the curvature. Now we'll go back to, we still have this note. Right, principal unit normal vector. So let R describe a smooth parameterized curve. So I have a curve. Have derivative. The principal unit normal vector at the point P on the curve at which the curvature not equal to 0 is equal to this. And say what is S? Oh, S is the arc length. So how do we write the function in terms of the arc length parameter? Of course, I mean, instead of doing that, we can also do this, which is we find V and then find T. Once you find T, we find the unit normal vector. Not unit normal vector, principal unit normal vector. Right. So let's just quickly to say it, what happened if we want to write is a function in terms of s though. For that, let's go back to section 14.4, the end of section 14.4, which is page 44. So section 14.4, page 44. Earlier we have this curve, and we said find the arc length, right? Oh, find the arc length function. So that is the arc length function. Doesn't matter what we have t, the arc length is given by this. Now, right, I'll show the parameter is still in terms of t. So this is still in terms of t. Now if we want to switch in terms of s, we will write s equal to square root of 20t. So we show for t, s over square root of 20. And we just substitute back into the t. So now we can say the curve in terms of s is equal to 2 cosine. Instead of t, use this. And then 2 sine 1220. And then 4 times t, which is that. So, what's the big deal here? It's not much. What we have here is, let's say, I just want to find the position. The function is in terms of the arc length. Like you can ask, where is the point when the length is equal to 5, for example. In that case, we have the length of the curve at some certain point, and then if we know the length, we know the position as well. So that's what it is. So if we want to, we certainly can do that, and we write that in terms of s, and well, that works out just fine. Like I said, there will be 10 or 15 different ways to calculate the curvature, and of course there are a lot of ways to do this. Right. So the note, curvature tells how fast a curve turns. The principle more is the direction in which the curve turns. Right. Now, let R describe a smooth parameterized curve with the unit tangent vector t and the principal unit normal vector n. The dot product is equal to 0, which means they are orthogonal. So the unit tangent vector and the principal unit normal vector are orthogonal. And then because they just give the direction when it point inside where it turns. Right. Now, find the unit principal unit normal vector for the helix where that. So let's go back to the formula. What do we have? Let's just do this one so we don't have to find the arc length, even though it might not be as bad to do this. So notice if we use this formula, we have to find the kappa, the curvature, and then that. Doesn't look like it's convenient enough, but we can use this formula. Unit tangent vector over dt magnitude over unit tangent vector derivative of that over dt. Now first, what is the unit tangent vector? Is that, so let's write as well t unit tangent vector derivative over the magnitudes of the derivative. So first I'll take derivative. A negative sine t, a cosine t, derivative of bt is just b, negative a sine t, a cosine t, and b. And then we just find the magnitude, divide them to get the unit tangent vector. So the magnitude square root of that and then a cosine plus b square. So we have a square sine square, a square cosine square, and b square. Sine square plus cosine square is 1. Factor out, we have a square. So this is just a square plus b square. And we divide them. Don't worry, a and b are just constant. So when we take derivative, it's not going to get any, it's not going to be very bad. So unit tangent vector, do that derivative of the velocity or the tangent vector over its magnitude. Once again, the notation is very important. This is just regular a, which is a constant, positive constant. Yeah. A and b are just constant. We're not going to worry too much about that. So negative a square root of a square plus b square sine t, and then a square root of a square plus b square cosine t, and then b over square of a square plus b square. Right, so with that unit tangent vector, now we will take derivative with respect to t and then divide by the magnitude. So derivative of that with respect to t, once again this is just a constant, so we're not going to worry too much about that. And negative a, so our derivative side is cosine, so we have negative a square root of a square plus b square sine t. We should take derivative, right? And then derivative of a derivative cosine is negative sine, so we end up with negative. Sine t. Derivative of that is 0. Right. Finally, we just need to find the magnitude and divide them. That would be good. Magnitude. So square root of, that's 1 square, that's 1 square. Ouch. Where's the cosine? And then 0 square. So if a square and that square root and square, so square undo the square root, so we just have this cosine square a square plus b square sine square. Once again, cosine square plus sine square is 1. So this just gives us the width. So that just, oh yes, now I forgot, I realized I forgot one thing, so that's square root. So again, we will have square root of a square over a square plus b square square root, oh that's it, the bug I'm talking about, a plus b. That's a terrible way to write this. Anyway, just put the square root on the top, square root at the bottom. If this has more space, I'm not worried too much about what I'm going to write, but since the space premium, so square root on the top, square root of a square. Since a is positive, square root of a square is absolute values of a, which is a, because a is positive. And then we have square root of a square plus b square. And then we divide. So we'll take that by this. I should get more space for this problem. Finally, principal unit normal vector. Again, that is the bone face n. There's no magnitudes on the top because that is the vector. Sorry. Okay. Otherwise, it's just one. Right. So, principal unit normal vector, derivative of the unit tangent vector over the magnitude of that. So derivative will be this, and this is the magnitude. Right, we're good, right? So derivative negative a square root of a square plus b square cosine of t negative a square root of a square plus b square sine t 0 all over that a square plus b square multiply reciprocal square root of a square plus b square over a, and then those vector so when we multiply it in, square root cancel square root and a cancel out, right? So we just left with the negative. So when we do that, we're left with negative cosine t, negative sine t, and then 0. Right, I should leave more space for this problem. Oh, write smaller. Right, but that's what we have. And because it is the principal unit normal vector, one thing I'm sure is this is the unit vector because the length of this one is 1. cosine square plus sine square is 1. So at least we got the unit part correct. That's one I'm sure of. And then the other one was principal unit normal vector. So what do we need this? It says the acceleration vector of an object moving in space along a smooth curve has the following representation. So now we can represent the acceleration in terms of the unit normal vector, the principal unit normal vector, and the unit tangent vector, and we have Hn and Ft given by those. Right. Since the complication is a bit complicated, we're not going to do any example on this, but know that acceleration will be decomposed into two components, and of course we did mention that they are orthogonal to each other, right? Yeah, on the previous page. G and N are orthogonal to each other. So we have a vector we decompose into two orthogonal vectors. So it certainly has some application to that, but certainly the computation is very complicated. So we're not going to do that. We just say, yeah, we can do like that. Right. So as mentioned before, it's not going to be a very long section, and so that's all we have here. As always, thank you for watching.